Alright, so hi all, and welcome to this last video. I'm happy to report, as I'm sure you're all happy to hear, last video on PDEs, on our course. So in this video I'll just do, I'll finish the course just by doing a sort of a variation on the heat equation. In a typical semester we might have had a little more time to get to the wave equation, which is usually the one that comes after the heat equation. But honestly, if you sort of done one of these PDE, famous PDEs and how to solve it and all of that, the rest of them are all very similar. I think I may have mentioned this earlier. It's really just a question of different ways of doing the Fourier coefficients and which ones you need and which ones you don't need, and more of these sine and cosine and pi over L thing. So so the rest of them, all like I said, once you've done one, once you have become somewhat familiar with Fourier series and Fourier coefficients, it's really the same theme for all of them. So you get some other neat graphs and other neat behaviors when you're modeling other physical kind of thermodynamical things. The wave equation is just what it sounds like. It models a wave, like an ocean wave, right, or other sound wave, anything that travels in waves. It provides a PDE for, and the solution to it actually looks very similar to this one, except you have sine and cosine, and so it just actually is. I can say this safely now, since we're not actually going to do it. It makes the problem just not any harder, but twice as long. So we can all appreciate that these are long enough as is, right? So anyway, so it's not a bad thing that we're not moving on too much with the rest of formal PDEs. And I think I'm sure I've said this as well in the past. Solving PDEs by hand, as we've been doing, is really not done because it's just, there's so much. We're not even really solving 100%, because even when we come up with these coefficients, these Fourier expansions, we're chopping them off, right? We're approximating anyway. So suffice it to say, this is great. You have a better foundational knowledge of PDEs than most people who work with them do. But solving them in practice is done via MATLAB or other numerical solvers, right? So anyway, so having said all of that, let's get at least one variation, though, of a heat equation model. I think you see some in some of the review problems where I throw some new things at you. By new things, I just mean other variations, right, or modifications of the heat equation, and lead you through some variations, in that regard. And that really is, right, again, aside from saying that all PDEs are kind of similar in terms of, solving with Fourier series and whatnot, even non-heat equation, or just any PDE, you more or less try to say, or try to envision it as a version of the heat equation, or the wave equation. These little variations are actually pretty good at getting to other problems as well. So we'll do one variation, though, together here, which is one that maybe occurred to you at some point as we were deriving all of this stuff in the last few weeks, which is the variation of the heat equation where what if the temperature on both ends isn't zero? Maybe this didn't keep you up at night, probably, but it's reasonable to be a little curious, at least, about, well, what if they're not zero? That's reasonable. And what if maybe they're not even equal? So what if you have one end of the bar is hot and the other end of the bar is cold? And we did an example problem of that, but that was talking about the interior of the bar. But what if actually the temperature on the ends of the bar, right, which we've been assuming are zero, what if that's not true? So we'll take us through a derivation of how to solve that, which will have some nice little nuggets actually about the heat equation in general that this will help us to discover, I guess. So we did these two examples last time. This one was sort of a nice, easy a constant temperature of, we chose 8 across the bar, and we solved it. And I graphed a few of these for you, and we did a little discussion of how the graph, aside from maybe the very first curve, pretty accurately represents what we think happens to heat when you have a bar that is a constant temperature of, we chose 8 to start with, all across the bar, except on the ends, right? In this example, we of course were assuming that the ends are 0. So of course, naturally, and by that I mean, we sort of have an assumption of maybe that it's sitting in a environment where the temperature is 0. So of course, what happens is that the ends cool off very quickly, which we could see that, the end which started at 8, down towards this left end, it was about 8, or close to, or was 8 when we started, but very quickly that cooled down to 0, or well, close to 0 anyway. Whereas, say, the middle of the bar takes a lot longer, right? And after the same short amount of time, the middle of the bar is still pretty warm, whereas the ends have cooled off much more quickly. So that agrees with our intuition, I think, about what happens with heat. Of course, in the long run, this whole thing is eventually going to flatten out, and it shouldn't be a mystery to anybody that the limit of this would just be 0. That the temperature across the whole thing eventually is heading towards 0. Because, of course, right, this is the way heat goes, right? Eventually, something that's hotter than its surroundings or colder than its surroundings eventually just reaches the temperature of its surroundings, right? So, which in this case would be 0. Okay, and then we did this other variation, like I said, where we had a cold left half and a hot right half. And the only difference that made it didn't make it too much harder to solve. But then we get this sort of cute other picture where half of it was hot and half of it was cold to begin with. And we again see that the heat flows kind of as we would expect. The hot end takes obviously a lot longer. Some of the heat from the hot end spreads to the cold end. So some of these first curves where it's actually heating up and then eventually cooling down is kind of neat to see, I guess, right? You can see that in the graph. We know that that happens in real life, right? That something that's hot goes up against something that's cold. It's not as though the thing that's cold stays its cold temperature the whole time. Some of the heat, as the hot part is cooling, some of the heat is actually spreading to the cool portion and actually warming that up. And we see that here. Okay, so these were our 2 examples, but those were just straight up the heat equation was the PDE, and there wasn't any variation on the actual setup, right? But what if we do vary this, and instead of just talking about the about the temperature on the interior of the bar, what if we talk about the temperature on the exterior, right, on the ends of the bar? What if those are different? So we'll do this one variation on the heat equation. Which is where we will assume, so let's take the standard setup. So we have our PDE, same as always. With an initial boundary condition, f of x. So that's our temperature profile at time 0. Okay, so that's our temperature when the experiment starts, and that may be whatever it may be. All right. I'm sorry, right, and of course we're doing this on still x between 0 and L. So we'll still say the bars of length L. So all that's the same, nothing's different. However, but let's assume that the temperature on the left end of the bar is, I'll just call it maybe capital T1, and the temperature on the right end is some other temperature, T2, and that's for all time. Okay, so I haven't drawn our little picture in a little while, so let me draw the little diagram that we might use just to summarize what we're trying to do here, or what we're saying. So if I imagine this problem is sort of existing in a box here, where the bar is down here, so this is the x-axis, and this is us saying the bar lives between 0 and L. Okay, but now instead of us assuming that on this end that the temperature is 0, we're going to assume that the temperature down here is whatever T1 is, some temperature. And let's assume that the temperature on the other end is some other temperature, we'll say T2. And that's true for all time. So in other words, we're assuming, you could sort of imagine that this is a long bar, and that maybe the right end of it is in a freezer, but the left end of it is in an oven or something like that, right? So you may have a hot temperature on one end and a cooler temperature on the other end, or vice versa, right? Okay, so then what we're really trying to study here is to say, well, f of x, that still describes the initial temperature, right? So f of x is going to describe what's happening at time 0. So here's our usual diagram here, right? That's time 0. But I want to sort of figure out what's happening as I go through time here. Well, f of x tells us about time 0. I don't know, just make something up here. Let's say that the temperature looks like that at time 0. Then the question is, right, what is it at time 1? And what is it at time 2, and so forth? Now, we had some nice symmetry going before, because we were assuming that the temperature on the two sides were both 0. So in these examples, well, especially the first one we did, I mean, this is 100% symmetric, because there's nothing different about the left side versus the right side, and in fact, they're both 0. And since the initial temperature distribution was symmetric, the whole graph itself is symmetric. This graph wasn't symmetric, or this second example wasn't symmetric. However, there was no rhyme or reason between the left side versus the right side, except for the fact that we had a different temperature. We had a hot end and a cold end on the interior, but the outsides were both still 0. So while that, of course, affected the initial temperature being hot on one end and cold on the other, affected our graph, but the outsides are still both 0. So, but let's imagine a situation, right, where maybe these temperatures are not, first of all, that they're not 0, and second of all, that they might be different than each other. Well, of course, that's going to have some influence over what happens as the temperature, as the heat spreads over time. Of course, it matters what the ambient temperature is in the room on both ends of the bar. But as we're going to see in a minute, or in a few minutes, this actually isn't that big of a adjustment to be made, and we're going to have a very cute trick for how we're going to deal with this. All right, so I just want to make sure we're all on the same page here. So here's our sort of quote-unquote new ODE, I guess, or our new setup is, and the only thing that's different, right, just to make sure we're all happy with what those two things mean, right? So this is simply saying on the left end, the temperature is T1, and on the right end, the temperature is T2 for all time, right? In other words, this is the room, so to speak. So that doesn't matter if I'm talking about initial time or later times or whatever. Okay, so how do we solve this, or how do we get at this? Well, let's make an observation, and maybe it's something we didn't talk enough about when we were just doing the general solution to the heat equation. But I think it's safe to say that, So I think we can assume that in the long run, in other words, as time goes to infinity, or not infinity necessarily, but at least as time gets big, we expect that the temperature profile reaches an equilibrium. Okay, so jot that down. What do I mean by that, or what is that saying? So this is very natural, so don't let this lingo bother you here, right? But what's the idea? So you're running any of these experiments, including this new one, but the old ones that we did, I would still assume that this is true, which is to say, all right, you've got this experiment, and you got some hot spots and cold spots, and temperatures here, okay, go. And it goes, and it runs. And as time goes on, of course, the heat does what it does, but eventually, in the long run, this eventually settles into what I think we usually refer to as an equilibrium, or at least sort of settles into a sort of permanent state, I guess you could say, or in other words, there's no longer any heat moving around at some point. In the long run, the heat settles and the temperatures settle into whatever they're going to be. Now notice that was true in the example. Sorry, I keep flashing back to these, right? But in both of these examples, I don't think we necessarily said a lot about this, but this is a super easy question, an easy way to earn some free points if I ask you. I mean, what's happening to the temperature in the long run? I mean, we could either look at the graph, which, the temperatures, right? I'm going from blue to red to yellow, okay, and then these are the graphs as I march closer and closer. I mean, of course, eventually, in the limit, the temperature is going to eventually just be flat. It's going to just be zero everywhere. Well, that makes sense, right? Because this whole bar is sitting in a room of temperature 0. Okay, that wasn't that surprising. You could even see that from the solutions. I know nobody wants to look at this solution, I'm sure. But as t gets big, if I do force us to look at it for a brief second, what's happening as t gets big? Well, look, all of the exponents are negative. So, of course, as t gets big, e to the negative big is 0. So what's happening to the temperature as time gets bigger? Every single term is heading towards 0. So of course it makes sense, right, that in the long run, the temperature across the entire bar is eventually settling into an equilibrium of just 0 everywhere. And the same thing is true even in our other example that we did last time, right? Eventually, even though this has a more interesting wavy kind of thing going on here, eventually what's happening, well, as I read down these bars, eventually, isn't it true, that I'm settling into just once again, oh gosh, that's a bad horizontal line, but I'm eventually just settling into these are eventually just going to be asymptotically close to just 0 across the whole bar. So this is not a crazy statement I just made, right? So this statement here is just saying, yeah, of course. Well, you're not, right? Eventually this settles into whatever it's going to be. Right? In those examples, it's settled into being 0 everywhere. But in these examples, it's not going to. Right? Maybe I shouldn't give away the surprise, but remember, in this example, I have some temperature on the left end, some temperature on the right end. Well, eventually it's going to settle into an equilibrium or a limit. But since these ends are not 0 anymore, I don't think I'm going to end up with just 0 across the whole bar, but I am going to end up with something probably related to these two temperatures. But let's investigate and see if we can come up with what that would be. And the answer is going to surprise you as to how easy it actually is. All right, but this is a reasonable assumption here. Okay, so let's introduce then, since we do think that it's reasonable for us to say that this is going to happen, and it will, that we will eventually reach an equilibrium. That's not going to depend on T, because again, that's the whole idea here, is that this is the temperature in the long run. So in other words, I'm not having to worry about, is T1 or is T2? No, whatever, just in the long run. Or you could say T is infinity if you'd like. But the benefit of this is that we're just going to have to deal with a function of x rather than a function of x and t. So let's assume that eventually, which means in the long run anyway, the profile is given by just a function of x. And so we're going to introduce notation. Let's use v. They seem to like to use v, I guess because we used u for the initial thing. But v tends to usually be the letter of choice for variations of these guys. So let's say let v, put better English here, so let v of x be the limit of our solution. Okay? All right, so in other words, v of x is this equilibrium temperature profile. All right? And again, it's v of x because I'm taking the limit as t goes to infinity, so I'm just left with x. Now, it may depend on x. It's not always going to be like these examples we did earlier. Oop, goodness. Where at the end of the day, the limit was just the zero function. In other words, it was just one, it was zero everywhere. Well, it doesn't necessarily have to be the same everywhere. So it can depend on x. It could depend on where you are on the bar. So that's why we're calling it v of x rather than just a constant, because we don't know that the temperature across the entire bar is eventually going to be constant in this situation. Okay, but let v of x be that. Fine. Since it's a solution, it's, a limit of, right, u of x and t, that's the solution to the PDE. Well, the limit of a solution is still a solution. I'm just sort of asking where are my solutions going. So that should still be a solution. So since v of x is a solution to the PDE, we know, so remember our PDE all along, is ut equals, I'll just write it down, alpha squared uxx, right? That's the heat equation. But v, since it's just the limit of the solution, is also a solution. But of course, what would happen when I run v through it? We know that, right, so if we run it through, okay, I'll do it this way so you can see. So, right, v of x is a solution to the PDE. So we know we could plug it in. Here, I'll do it this way, right? So when I substitute this in, I should get a truth. Okay? Well, okay. But what does this mean? Well, first of all, this is like a happy moment on the left here. This says v, which is a function of just x's, you'd like to do the t derivative of that. I'm pretty sure that if you do the t derivative of something that has no t's in it, you get 0. Think about that for a second, right? But that's true, right? V of x has no t's in it. So if I take the t derivative, everything is just a constant. And like a derivative of a constant 0. Okay. And I don't really need this archaic notation, because since v is just a function of x, we can go back to our more familiar happy notation that the xx derivative of a function of x's is also known as just the old second derivative. Okay. So we have this. Obviously, I could divide both sides by alpha squared, which tells me, of course, that v double prime is 0. All right, I'm going to need a little more space here, so actually I'm just going to go to the next slide, so keep going, though. So, of course, after I divide by alpha squared, I end up with that. And this is just a simple ODE now. Right? V is just a regular old function, and I happen to know that its second derivative is 0, so we could, of course, think about this for a second and come up with a solution if we want to do this more formally. If we integrate once, right, so integrate once and you get a constant. Integrate one more time and I'd get a line. Right? So, of course, a line, which is what that is of course, the solution to to a function whose second derivative is 0. I'd have to say, well, it could be a constant, right? But I have at most a line in here. Okay, so this vxx, which I should pause here. Hopefully I didn't lose anybody here, right? I did one integral, and then I did another integral, which gets me to v, right? So this v, but remind ourselves, wait, but who is this v? Oh, that's right. V of x is it's any of these things we wrote down. It's the equilibrium temperature profile, which sounds fancy, but all v of x is it's the temperature, it's what's the temperature going to look like in the long run. Well, what does this say? This says, first of all, the temperature in the long run is going to just look like a line. Right? This is just a line. It's just the equation of a line. So, right, so v of x, now that's not the solution. I mean, I haven't solved the PDE exactly, because I don't know what, I mean, I know what v of x is, I guess I should say, and we're going to get even fancier with that. Now, I don't know what u is. I don't know what the solution to the PDE is just yet. But at the very least, I could say the equilibrium, because I haven't actually tried to solve the PDE just yet. But the limit of the solution, which we've yet to produce, is actually just a line. And even better, what do we know is going to be, right? So this is just a line. And remember, since v of x, maybe I should put some more words here. But since v of x is the temperature profile, in the long run, we know two things. We know v of 0 should be temperature 1, and v of L should be T2. Let's just make sure we all agree with that. So, right, so V is the temperature profile. By temperature profile, I just mean the graph of the temperature across the bar. In the long run, well, we already know, remember, this is our setup for today, that we have this setup for our PDE, that on the left end, you could say the temperature of the room, right, or of the end of the bar, is always T1, and for the right end, it's always T2. So I think it hopefully makes sense to say, obviously, or it does make sense to say, that in the long run, what's the temperature on the left end? Remember, that's when x is 0. It should be T1. And what's the temperature on the right end? That's when x is L. It should be T2. So that's all I wrote down on this slide here. Right? So temperature, V, in the long run, on the left side, that's 0, is T1, and on the right side is T2. But this is going to, of course, tell us immediately some good stuff about V. So, of course, let me put a box around that. So the fact that V of 0 is T1, though, isn't that going to immediately tell us something pretty good? So if I run 0 through that, of course, I would say, oh, that means T1 is C1 times 0 plus C2, which, of course, tells me that C2 is T1, which is a little funny. But the letters are like that, but that's all right. Okay, so far so good. So that's I'm halfway there, right? So now, since I guess I'm trying to figure out what V is, well, I know that the C2, the number over here, is going to be the left-hand temperature. Okay, but now I can use the second fact. I know that when I plug in L, I'm supposed to get T2. So I'm going to get T2 when I plug in L. Okay, so of course, but I know already that C2 is T1. So this is C1L, but C2 is really T1. Oh, that's me just using this fact up here. So of course, if I rearrange this a little bit, I get what? T2 minus T1 over L is C1. So I get some pretty easy numbers. Remember, these are numbers, right? T1 and T2, those are temperatures. Temperature on the left end, temperature on the right end. L is the length of the rod. So you certainly know how much C1 and C2 are right from the beginning of the problem even. All right, and so I'm just going to jot my summary here in the corner then. So pulling all this stuff together now, we know now that V of x, which again, that's the temperature in the long run, is simply, we already knew it was a line, but even better, we now know that that's the slope of the line, and that's the y-intercept of the line, if you want to go way back to somewhere. Maybe let me unbox that since we improved upon it over here. Oh, okay. So this, I didn't do anything here except some really simple algebra, or a little bit of calculus up there, but we actually get a very nice thing, which is that, so let's come back one last time to this slide. So V of x, which is telling us what's happening in the long run. Well, in the long run, this is just, the temperature profile is just a line, and in fact, it's this line. Okay? So, well, we love lines in some sense, right? We love them in the sense that they're easy, right? It's easy to work with, they're easy to do math with, they're easy to do algebra, whatever, right? So here's the clever observation that we're going to make. So we haven't actually solved the PDE yet, right? So I'm still stumped right from this, right? I still haven't actually solved this PDE, but we've sort of done a weird, I don't know what the right word would be. We've solved for what the limit of the solution is, which is a little bit like backwards. Usually we get a solution and then we ask what the limit is, but what we've actually done is we've found the limit, and now we just need to somewhat backtrack, I guess, and figure out the solution who has that as a limit, I guess I would say. And here's where we make a very simple observation. So I'm going to go back to one of these examples, so we have a graph in front of us. We know that the heat equation, just the regular one here with the zeros at both ends, eventually the temperature settles to just be zero everywhere. And that, this is an incredible amount of fancy math, as you've experienced over the last few weeks, in order to derive the solution to the heat equation and to get these coefficients and all of that. But one thing we can say for sure is that we know that this process of heat diffusion, in a situation where the ends would be zero anyway, eventually settles down to just zero everywhere. So, in order to solve the heat equation with unequal temperatures on the ends, I'll just repeat that piece, right? With the temperature on the left end T1 and the right end T2. Let's do our very favorite thing. Oh, it's nostalgic. It's our last one, but let's make a guess, and we'll plug it in, and we'll see what we can say about our guess, right? Which is literally the only strategy in all of differential equations for the most part. So one last time, here we go. Let's make the following guess. All right, so since we're trying to solve the heat equation, I'll go back to U, because that's our goal is to solve the heat equation. So our guess here for U, right, for a solution. Well, let's guess the following. So I love this V that we just computed in the most basic way. So let's guess V as part of our solution. But since I know that's not a fact right there, well, the limit of this equals that. The t limit, right? As t goes to infinity is that. But that's not going to give us the solution at all t. That's V of x just gives you the solution when t is infinity. So let's allow ourselves to have maybe some other piece. So we'll use W since that's in the right vicinity of the alphabet. So let's guess, let's make the following guess, right? So we'll guess that U, a solution, is made up of, this is the long run profile plus an unknown helper. We always like our little helper guys. So this is our guess. So our guess for the solution of this modified heat equation with the uneven temperatures on the ends is to say, let's guess that it's made up of the sum of the limit, right, the long run profile, which we already know that, plus a helper, an unknown helper. All right? Well, what do we always do? When we make a guess, we plug it into the PDE, and usually good things happen. All right? So if we plug our guess into the heat equation, I'll just repeat it for you one more time. UT equals alpha squared UXX. What do we get? Well, let's see. So I'll start here. So I get, so this is our guess here, V plus W basically, right? V plus W is our guess. So V plus W, I'll write it all out here for us. I want to do the t derivative of that, and that supposedly is going to equal alpha squared times the xx derivative. So, okay, so that's V of x, and W of x and t, and the xx derivative. Okay, so I'm going to do a similar thing here, of course, which is where I'm going to take a little bit of advantage of the fact that v is just a function of x. So if I try to do the t derivative on the left here, well, this has no t's. Now this does, so I can't just ignore the w piece, right? But when I do the t derivative over here, this is going to be 0, and that's just, I'm going to suppress a little bit of this now and say that's the t derivative of the w function. Okay, so that's my left-hand side. Now my right-hand side, okay, alpha squared's a number, and now I got to make sense of this. So the xx derivative of these. Well, these, you know, this has x, v of x obviously has x's, and so does w. So neither of those is negligible, or in other words, I have to account for these. But what did we just say about v? I'm sorry, yeah, v. We just said in our little derivation that v double prime is 0, right? Or maybe I said it, well, no, I didn't really say it anywhere else, but there I said it. So v double prime, right, the second x derivative of v is actually 0. Okay, so maybe I'll put a star there. So, oh, well, that's going to appear right here because I'm about to do the xx derivative of these two pieces, right? So I'll write it out so that, oh, right, I don't really need to say that, right? Because again, it's v. It's a regular function. It's a function of just x. So why don't I do v double prime? The w, I'll leave in our traditional notation, right? Okay, so that's just me acknowledging that the xx derivative is just a regular second derivative for v, whereas it's the xx derivative of our mystery function w. But this is 0 by the star comment from a slide or two ago. Okay? Okay, which means that's going to drop out as well. And so I'm going to go to the next slide, but just keep going here. So what am I left with? I just have wt equals alpha squared times wxx, which should look awfully familiar. So all we're left with is this. Which means our mystery helper is simply the solution to the heat equation. And I'd say, wait a minute, I thought we were solving the heat equation. Right, but let me, so I don't want to lose anybody here, right? So we've done this a million times, right? We make a guess for a solution. We plug the guess into the PD, in this case, the PDE. And, you know, whenever we do that, right, we're always trying to sort of force something to be true. that we can hopefully then solve, right? So we're trying to force, and in this case, it's our unknown helper is who we're trying to force to be a known helper instead of an unknown helper. In other words, we're trying to say, well, who is this mystery W? Or what has to be true about this mystery W in order to make the guess a solution? So we ran it through, and this all boiled down to us saying W has to satisfy this. Well, that's just literally the heat equation. But, right, okay, but we're in the process of solving the heat equation with these uneven ends. So this is where we reach the point where we're just like, ooh. So I was trying to solve something, and I got that the solution to my problem is the solution to my problem. Ooh. Well, that's like a 1 = 1 kind of scenario. So I'd be dead here if I didn't finish my thought here, though. So U is the solution to this version of the heat equation. But W, while it has to satisfy the heat equation PdE, right, that's what this boiled down to, let's check on the ends. So what's the temperature on the left end? Or what do I get when I plug in 0 for X and any value for T? Well, W was simply, remember, W was simply V. Let me come back over here, right? This is my substitution here, or this is my guess, right? U is V plus W, so obviously that's equivalent to us saying W is U minus V, right? So I don't want to confuse anybody here, right? But if I want to talk about W, I could obviously say W is simply U minus V, right? So, so W at some time, W is simply U minus V. Right? I feel like I should say that, right? Since just by definition, right? W is literally just defined to be U minus V. Okay, from the last slide. That's our guess. Okay, so in particular, if I plug in 0, which is the left end of the bar, I'd get that. Fine. But the left end of the bar, U, remember, U is the solution to our adjusted problem. The left end is always temperature T1. And how about for V? Oh, well, we just said that too. V at the left end is also T1. Oh. Oh. Okay. So W, while W has to satisfy the heat equation PdE, the temperature on the left end of for W is 0, not T1. And then similarly, if I do the other end of the bar, I'll just fill this in for you. I get that, of course, but these are both T2, which means, oh, I am not in trouble here, because let me pull this all together. W, oh, yeah, okay, W, our mystery W, is actually just, I could say the, or maybe I'll say the. Oh, I'm sorry, I'm not ready for my conclusion yet. Sorry, let me do one more thing. So far this is looking good though, right? So W solves the heat equation, but has 0 temperature on the left and right ends. Well, we're all experts in that one now. That's the one we've been working on the last few classes, right? So since our goal is going to be to eventually figure out who is this mystery W, this is looking pretty good, because this is just saying, oh, hey, this is just like a problem like the 2 examples that we did in the last video. But there's one piece missing, right? So in order to solve any PDE, I need to know, or the heat equation anyway. Okay, so I got the temperature on the left and the right are both 0. But remember that one other thing I need in order to actually solve this is, what's the initial temperature profile? So I need to know, how about what's the temperature at time 0? Right, that's our little f of x that we've been using, right? And then we know that that's the most important piece of information for actually solving the heat equation. It's because we use it to do the Fourier coefficients, right? Okay, well, let's see how much this is. So that's u of x and 0 minus v of x, obviously. say, well, u of x and 0, that's the initial, times 0, right? That's the initial temperature across the bar. Well, we've been calling that, as we did in this problem, little f of x. And v of x, we know what that is. Okay, so just so I'm pointing to you to all the right things here. When we state, oh goodness, it's way back here. When we stated this problem, right, little f of x is still the initial temperature distribution, whatever that might be. But now along the way we've discovered a nice easy formula that says v of x is that, okay, and as it turns out then, for w, this is, what's the initial temperature profile for w? It's just the difference of the initial temperature for u minus this equilibrium solution. All right, so this is known. This is the original. This is the initial boundary. So you have that. This, we know this one too. Via the formula that we just came up with, right? T2 minus T1 over Lx plus T1, I think. T2 minus, yep, that one, okay. So, check. So let's pull this all together now. I'll just stare at this slide one more time. I'll write it down, a summary for you. So, actually I'm going to cheat and go back. Aha, all right, so to solve the heat equation with these uneven temperatures on the ends, we have made a guess, and we have good news. This guess u that's going to solve this guy, the one with the uneven temperatures, this guess is going to work as long as v is given by the formula that we've discovered, so that's it, that's done, we know that one. And as long as w satisfies everything you see on this slide. So let's read this from top to bottom. First of all, w has to satisfy the heat equation PDE. W has 0 temperature on both ends. And the initial temperature profile for w, for the w problem, is simply the difference of the initial temperature profile for the u problem minus, once again, this v function. All right? Thus, our guess of u works if, I'm being really repetitive here, if v of x is this, maybe I should say works with, v of x is given by that, and w solves this heat PDE. Okay, where all of the stuff is the same. Zero is between, x is between 0 and L. W on the left side is 0. W on the right side is 0. And most importantly, the initial boundary for W, I need a little more space for this one, sorry, is f of x minus v of x. Sorry, I'm really badly lining these up here. Yeah, let's do it this way. Okay, so in order to solve this new problem, this uneven temperature on both sides problem, I have to do algebra 1 or algebra 2 in order to get the equation of that line. And I have to do, well, okay, right, I do have to solve a PDE, right? But this is one we already know how to solve this one, right? Let me just emphasize this, right? This is just the regular we already know how to solve the 0 on both ends version of the heat equation. So we know how to do W already, is the point of... Now, that doesn't mean you know what W is, right? You got to actually solve this, right? So obviously, I mean, if I misled you to believe that this wasn't going to involve doing an awful solving a PDE problem, no. Okay, it does, right? It's just that the good news is that to solve this whole new kind of PDE, or this whole new kind of heat equation PDE, all I really needed to be able to do was solve the one that we already knew how to do. And then I'm going to make this small little adjustment. Okay? So we did a couple examples, right, where, I mean, what's the only thing you're really even extracting out of most of this? Obviously, you're extracting the alpha squared, and you're extracting the L, and you're going to need the T1 and T2 in order to get the parameters here. That's all easy. But then, of course, yes, right, you have to actually solve this. And then, of course, in this case, the what we were calling f of x that we were using for the Fourier stuff is now, that's my new f of x, is that it's the f of x that's actually the initial temperature profile for the problem minus this equilibrium temperature profile. So it's a very cute trick, right? And in fact, all it's really doing is it's sort of stripping away, or it's isolating the equilibrium portion from the what we may call transient portion. So maybe this isn't that surprising that solving this is no real harder. It's not really any harder than solving the one that has 0 on both ends. So I'm going to just do an example, and by do an example I mean I'm going to state it and write down some of the details, but I'm not going to solve yet another heat equation problem since it's just, nobody really wants to see that at this point anyway. But let me at least give you a problem that's fully stated, and we'll do the V part and all of that, and then I'll sketch some graphs for you as well of what the solution would look like, and then I think we'll call it a day. So let's look at an example. So suppose, let's start this, get this whole thing down here for us. So let's try one where so consider the heat equation. So UT equals, and in this case we're going to make, I'll put a 1 here, but we'll make alpha equal to 1. I'm not actually going to solve this, or I copied this out of somewhere, I'll be honest with you. So they solved it, so there was a 1 there, so fine. So alpha squared is 1, or alpha is also 1. On the interval, since we've done so many problems where 2 is the length, let's at least pick one that I'm doing 0 to 30, so L is 30. So it's a 30, the bars of length 30. And let's say that the temperature on the left side is 20, and the temperature on the right side is 50, and that's for all t. Okay, so we're going to set up a problem here with one of these uneven temperatures on the ends. So the left end of the bar is 20 degrees, and the right end of the bar is 50. So obviously the left end is the cool end, I guess, or the cold end. If this is Fahrenheit anyway, 20 is definitely cold. 50 is maybe just sort of cool or warmer at least on the right side. Okay. And the initial temperature, right, let me give it to you this way. Right, the initial temperature across the bar, which is our f of x, is given by maybe something like, I'll just go with a nice line here, 60 minus 2x. Okay, so that's all talking about about this heat equation, right? These are all of the details about the actual problem that I'm trying to solve here. Right, okay, so of course the question is, can we solve this PDE, right? So what's the solution? And we'll graph it and stuff like that. All right. So like I said, I'm going to do all of the new stuff from today I'll do, and then we'll just sort of punt on the actual solving of the PDE, and I'll skip to some graphs here. But so what's the solution? So if I was actually going to solve this from start to finish and from scratch and all of this, of course, I'm just going to pick out some details here, obviously. So that's, of course, T1, and that's, of course, T2. I already identified what L is. Now this is f of x, so I'm going to use that, or I need that, but let's see. So well, at least, right, I've picked up some things. So I think a good thing to do when if you're solving one of these all the way through, is to say, well, what's the solution? Well, we wrote down the nice solution. It's right here. It's v plus w, where v is attained via algebra, and w is attained via not algebra, because I have to do a solution to a heat equation, right? But let's do the easy thing first, right? So v, I can get v just by doing this. So let's do that first. So if I'm going to get this, so if I'm trying to get the solution, I'm going to do two steps. One is the easy step. Let's write down what v is. And v, I'm just going to copy this straight up for the millionth time today. V is just that. Okay? Why do I think I'm writing this down wrong? Is it plus? Oh, it is plus. Okay, sorry. It's being paranoid there. All right. Well, let's see. I could write that down. I could fill that in. So what do I have? I have 50 minus 20 over 30 plus 20. So that tells me V is, I forgot my X. So that's 30 over 30, also known as 1, plus 20. So what does this mean is that in the long run, the temperature profile across the bar is given by x plus 20. Now that's just a line. And in particular, of course, what's happening when x is on the left, when I'm on the left end of the bar, when x is 0, this is 20. And when I'm on the right end of the bar, that's 30. This is 50. Well, that's not a surprise. Of course, the left end in the long run, the left end should become 20, and the right end should become 50, because that's those are sort of the ambient temperatures on the two ends. So what's kind of interesting, though, right, is that this is saying what connects it. So actually across the bar, the temperature is actually just a straight line. And in reality, this is true. I don't know how you're going to do this experiment, at home. But if you were somehow going to be able to do this somehow, if you've got some way of simulating a hot end and a cold end, if you let it go for a while, the temperature across that bar, or whatever it is that you're exposing to this, will actually be a perfect line as you read it from left to right. And it'll actually just be literally this line. It's kind of, I don't know. I know this is all very complicated in some respects, but this is one moment where it is super not complicated. So you take a bar of a 10-inch bar, and you put one end at 50 degrees and the other end at 30 degrees. This line tells you the temperature across the entire thing in the long run. And it's just a line, right? So obviously the slope is 1. So every inch or whatever that you move across the bar, the temperature goes up by 1. So it's very simple, right? I mean, I don't know if you had any delusions or thoughts that there would be some sort of weird curvy behavior in the long run, but there isn't. It's just a line. Okay, so where is, of course, all the curvy, crazy stuff happening is in the second piece, which is that, right? So that's so in terms of coming up with my solution, I'm done with that. But now I need to know that, okay, of course, this is the hard part, which I'm going to completely skip here. And of course, W of x and t solves the regular heat equation with initial boundary given by, I'll go to the next line. With initial boundary condition of f of x minus v of x, which for us, well, f of x, that's given up here, 60 minus 2x, that's f of x, it's right here. Minus v of x, we just did that. Okay, so obviously here, what I have 40 and negative 3x. So all you have to do to solve this is do the solution to the heat equation, which we've done to death now, or at least the strategy for doing it, where this is the quantity that you're going to use to do all those awful integrals. Which is why I'm not going to do this problem and instead say, sure, right, this is going to just turn into a similar kind of wavy heat thing, so I'm just going to pretend for a minute that we actually solved that. You get something like one of these, right? And probably not so much that one. Probably a little more this one. But slanted, right? Because the initial temperature that we're using, or the initial proposed temperature profile, is the equation of a line, right? So it's probably going to get these sort of wavy, this wavy solution, but it's going to be on a bit of a line at first. Actually, probably it's closer. It is probably actually closer to this one. But what, of course, eventually happens with this piece of the solution, the W piece of the solution, is going to look like this, probably more so like the one we're looking at here. It's going to do its wavy thing for a little while, but as time goes on, the W piece is heading towards nothing. So in the long run, let me come back here. So in the long run, right, the W piece vanishes because the solution to the heat equation with zeros on the ends, in the long run, we know that that's just zero everywhere. And so in the long run, this whole solution, which remember is just the sum of these two, right? What do you get from part 1 plus what do you get from part 2? The W piece is going to vanish, in other words, just head towards 0. So in the long run, of course, it's just going to look like the line x plus 20, which we kind of already knew that, right? That's what v of x actually is. But that holds true here as well, right? So of course I'll just say, right, solve the Fourier. Okay. So then, I knew I was going to run out of slides. Let me just get one more here to draw you a cute graph. Oops. Okay, so if we actually solve that, right, so the solution is then my W, the V piece, which I'll fill in, that's x plus 20. Plus, I'm just going to leave this vague here, right? Plus the W solution. Okay, so that's the solution doing this awful problem at the bottom here. But one thing so the solution is that, right? So if you're writing down what's the solution, it looks exactly like the ones we've already done. But then you're going to throw in the equation of a line. Right? You're just going to add in whatever the V piece turned out to be. So this is the solution to the whole problem. But of course, this piece, right? We know that this goes to 0 as t goes to infinity. Okay, because this is the solution to a heat equation where you have zeros on both ends. So we know in the long run the whole thing's just becoming 0. So of course, in the long run, we get what we started with at the beginning, which is just the V piece. Right? I'll just remind you, right? That's V of x. Right? Or maybe I should do it over here. That would make more sense. Right. Okay, so we sort of came full circle here. We started by using the limit without actually knowing what it was, but now that we used it, it's always nice to sort of double check. Wait, do you actually get the limit at the end? Is what the thing you said was in the middle? Yes, you do, right? So visually, I'll just draw you a little sketch here of what this would look like if you actually solved it and were a fancy person and plotted this in MATLAB and stuff like that. Move that over a little bit. So here's time, and here's temperature. Oop, that's a 6. So let me try to be a little bit to scale here. 10, 20, 30, 50. Okay. So, if I was going to plot the solution, right, so this is us having filled, so let's pretend for a minute we actually filled in what the W piece gives you, and you go to plot this. I promise it would look something like this. So first of all, at time 0, what's the initial temperature profile was 60 minus 2x, right? So that was, not too far. This was the initial temperature, right? 60 minus 2x. So at time 0, I'll do this in red, and then I'll try to give you some other colors. So 60 minus 2x is just a line. Oh boy, hopefully straight. So that's at time 0. So of course, what's that saying? That's saying that on the left end, the temperature is, or towards the left end, right, the temperature is 60, and towards the right end, it's actually 0. Now we know that this thing is in a heating and cooling environment, right? Where on the left side, it's actually 20. That's T1. And I'm just going to do a little trick over here, which is to put the temperature scale over here too. And on the right end, I'm just going to do the same numbers here, 10. Right? T2 is 50. So squint at this for a minute, and then I'll write in the rest of our graphs. So when I start, the left portion, right, or the left half or whatever, is hot, and the right half is cold. But the hot end is sitting in a room of temperature 20, and the cold end is sitting in a room of temperature 50. Aha! So of course, without any science and just our intuition, we know that what's happening is that the temperature is going to sort of do a little switcheroo at some point, or sort of move towards, heading more towards agreeing with what's going to happen in the long run to this. So if I draw a few curves in for you, I am copying this from an actual solution, so let me try to get this sort of right. At time 5, the temperature looks like, I was going to do some different color. That was a good graph and everything. So let me go, maybe I'll go orange. So 30 to 40, okay. Okay, so that's the temperature at time 5. Okay, so after 5 seconds or whatever, the left end has cooled off quite a bit, because of course it's heading down towards 20. And the right end has warmed up quite a bit, because it's heading up here towards 50. But of course it's wavy, because these are sine graphs. I'm probably being a little generous with making the wave quite that smooth, but it's in that right ballpark. Let me draw 2 more in for you here. So I'll do green next. At time 10, it is looking like this. Okay, and then I'll give us one more, which is at equilibrium, or as time goes to infinity, it's going to look like that. Oops, let me not do that. And that's time infinity, and that's of course just v of x, which is just a line going from 20 up to 50. So this isn't as sexy as the MATLAB graphs, right? But they would look more or less like this if we actually solved this and plotted it formally, right? So the curves, right? So this orange one the red one is how it starts, and then of course, right, what's happening is that the hot end is cooling off. The cool end is warming up. That continues in the next 10, and then at some point, right, as time gets bigger, past 10, probably by 20 or 30, it's probably pretty much nailed onto this equilibrium line, this v of x thing, that is, but that we already knew was going to be the limit. Right, so it's eventually basically just smoothing out into a line, which is kind of neat, I think. I don't know. I think it's kind of neat. So let me end this so I stop writing. So that's it for us. So so for next week, there are already, as I mentioned before, some review problems, or I guess I'll call them multi-purpose problems, right? They're a review for the exam, they're homework problems, they're all of that. So check those out on Canvas. I think I posted them a few days ago, or at least a draft of it. I may add 1 or 2 more based on this last little bit of stuff here. But try them. You know, there's a lot in there. I will post solutions, probably not till, I don't know, the weekend. I should hopefully be able to get them done on the weekend. So check them out. It's obviously, probably goes without saying, you don't really want the first time you're trying these problems to be on the exam. I know that there's no web assigned for this to sort of, quote unquote, force you to try them, but I think you're all smart enough to know that you do want to give these a try, and make sure that you've worked out any kinks that you might have in solving them. So do check them out. Next week, I won't, this is it for material, so there won't be any videos for next week. But if you do have questions that come up from studying and looking over things, I'm obviously around next week to meet if you have any questions, or you can email me if you want. Although, if ever there was a subject that probably is pretty tough to convey in an email, it's probably stuff like this. But I will send you guys an email though, also with the format for the exam. At this point, since our last class is Thursday, the 14th, I guess it is. It will be on that Thursday, the 14th. At this point, I don't have an exact number for you, but I think that rather than trying to do it in the hour and 15 minutes or whatever our time period is, I mean, you can't even get one of these problems off the ground. Well, you can in that long, but you know what I mean. These are long. So I'm going to do some sort of here's the thing, and you can take some time, more than just the hour and 15 minutes of class. I'll look at it, and I'll look at the exam. I know you're probably like, oh my God, this is going to be impossible, and this is going to take too long, and how could we ever do this? But just, have some faith in the fact that I can ask you questions in a way that you're hopefully not having to solve an hour-long problem for each of these things, and instead split it up into pieces so that I can at least see that you know what you're doing, and things like that. So yeah, so do try these over the weekend, like I said, and I will be in touch with some details about next week, and certainly about the exam. So, but have a good weekend, and I will talk to you next week.